CHEM152L. This is the Experiment 10 pre-lab lecture. A couple of reminders. The whole experiment is due a week after the experiment is performed virtually. So that's May 12th, the Tuesday, or May 14th, the Thursday, and that's at the end of the day that those are due. These afternoon office hours are wide open. You can get some one-on-one attention. Come see me on the Zoom office hours. You can talk about your experiments, talk about the pre-labs, post-labs, any of it. Come see me. And your lab assistant, that's Jamie for Tuesday or Care for Thursday, they're available. They want to answer your questions as well. So you have plenty of resources for getting questions addressed. And just wanted to remind you one last time, withdrawal date is May 8th. So you can see the end is near, people. We're doing experiment 10, then experiment 11. The last experiment is experiment 12, so we're on the home stretch. Today this talk is going to cover gases. So specifically we're going to talk about the ideal gas law and the important things from that, and then how you can use the ideal gas law to get all the other gas laws that maybe you've talked about in lecture. And then there's one other gas law outside of the ideal gas law derivations that we'll talk about, and then I'll go over the specifics for experiment 10. So the equation that you need is PV equals nRT. Okay, so this is gases. The variables we're looking at are the pressure, the volume, N is the moles, R is the gas constant, which is written here, and then T is temperature. Okay, I really want to emphasize, if you're in the gas chapter, you want to be in Kelvin units for temperature. So constantly, very first thing when you see a temperature in Celsius, go to Kelvin. That should be step one. The other units are shown here. So moles told you is N. Pressure has got to be in atmospheres when you use this gas constant, and the volume has to be in liters. So this gas constant units governs what units all of these are in using this equation. All right, so the other piece is the derivations. Okay, so what I encourage you is know the ideal gas law, PV equals nRT, and then read the problem and adjust your gas law. So you may have a problem that says there's an initial pressure, initial volume, what's the final pressure if the new volume is this? So you need to interpret that and say, wait a minute, these are constant. Your moles, your temperature, those aren't changing in the problem, and the R is always constant. So you can rearrange then and say, well, scenario 1, pressure 1, V1 equals this constant. Well, that's also going to be the same because by definition they're held constant, as if you change the pressure, then you'll have a different volume. Okay, so this, take away the constant, that's Boyle's law. P1 V1 equals P2 V2. So you saw that on the pre-lab assignment. Well, in my classes, you don't have to remember, is it Boyle's law, is it Avogadro's law, or any of this, but you just have to know, can I get to the equations that I need? So Charles' law, again, it's not important that you know who Charles was or any of that, but do you know how to get to a V over T and everything else is constant? So V over T, pressure, moles, those are constant. And remember, temperature definitely needs to be in Kelvin. In this case, you see right here, PV equals PV or V over T, V over T. You're not actually using the gas constant, so you could be in different units. You could be in milliliters for the volume. You could be in millimeters of mercury for the pressure. Okay, so that's not required for these other equations. It's just required when you use the ideal constant. So that should be going to here for milliliters, pressure. That's okay, as long as the units are in the same millimeters of mercury on the left, millimeters of mercury on the right, milliliters on the left, milliliters on the right, then you're all set. Okay, so that's pressure, volume, volume, temperature. I'll put a couple of others up here. But the main thing, again, wanting you to feel confident that these all come from the ideal gas law. So you're just rearranging. So here I've got volume and moles. So I'm rearranging volume and moles, and everything else is constant. Okay, so volume over moles, volume over temperature, pressure, volume. These are the derivations. And then on the pre-lab as well, there's a combined gas law. So that's PV over T equals PV over T. So you can see there's a lot of equations in this. It can be a bit overwhelming gases with all the equations, but I encourage you to start from ideal gas law and work from there. The one that I'm going to talk about that's not included on the ideal gas law is Dalton's law of partial pressures. Okay, so all of those above were pure gases, ideal. What I'm showing you now is a mixture. Okay, so this is a mixture of gas A and B, and as long as the units are the same, again, could be atmospheres, could be millimeters of mercury, you can add up the pressures of the mixture. So A pressure, B pressure, and that'll equal the total pressure here. So this is some of the equations you'll be using, and for sure the goal of this is to calculate R. Goal of the experiment is calculate R, so we're going to use this equation, but you'll see many equations in gases, and to calculate R we have to use this equation, so that's why I wanted to point this one out. So our experiment, this is actually a really good experiment. Students really enjoy this, and it goes quick, so that students enjoy that. But this is taking a nice piece of metal, magnesium, and you add hydrochloric acid to it, and you get magnesium chloride, hydrogen gas. Okay, so that looks like reactions you've done. However, the setup is very different. So watch a video, because you're collecting this gas, so you're assembling the metal so it'll react. The gas will go up in the tube, the eudiometer. It's a really interesting setup. Ours looks similar to the video. We just use a bigger beaker at the bottom. And the reason we use that bigger beaker at the bottom is right here in this note, okay? So the video is one step more complicated, and how we can do that is at Miramar, we take the height of the column of the liquid in the eudiometer. So what we're reading, where the glass is collected, we take that height and we make it level with the water surface. Okay, so the water surface and the inside liquid, that means the barometric pressure is equal to the pressure of the hydrogen plus the pressure of the water. So that's Dalton's law of partial pressures, and this one little difference is the reason why we have a simpler equation than the video. So if we were doing this on campus, I'd actually demonstrate. I'd show you how to clean off the metal, how to assemble it in the cage, how to react it with the hydrochloric acid, collect the hydrogen gas, and then I'd do a calculation and show you all the steps that you're going to do. So clearly I can't do the experiment here, but what I can do is show you the steps for the calculations. Okay, so if you see the video, it tells you your measurements. You need the mass of magnesium, okay? You need the temperature of the water, and we're assuming the temperature of the water is the same as the temperature of the gas. You need the volume of the gas collected, and that's inverted in that tube. It's a little tricky to make that reading, but you can make a reading of that. And this water vapor pressure is from a table. So you look up the temperature, and it tells you that on this table, the vapor pressure of water varies with temperature. So you look up 20.8 degrees Celsius, it's 17.535 millimeters of mercury. I checked the barometric pressure excuse me, on the wall, and when I did this last year, this is what the barometric pressure was. So these are the 5 measurements. Okay, so you can imagine if you got grams, this is chemistry, you've been doing this for a while, right away you want to go to moles. So that's our molar mass. of magnesium, and that gets us our moles of magnesium. Okay, well, we're not really interested in the magnesium, okay, but we have to get to moles of magnesium in order to get to what we are interested in, moles of hydrogen. So I know this doesn't change the value, but we're making it clear that we're converting 1 mole of magnesium to 1 mole of hydrogen. Okay, so you do this, and that gets you your moles of hydrogen. So you can check that, solve for that, and I'll show you here shortly what that is. Remember right away, if you see Celsius, you've got to get to Kelvin. So convert that to Kelvin. So you can see one problem has a lot of conversions. Make sure we're on the right units. So convert to Kelvin, good. And then that's milliliters, that's our volume. However, we need this in liters because again, this is solving for R in the units I showed on the slide before. Okay, so now our water vapor pressure and our barometric pressure follow this equation here. So that takes us with this 751 minus 5.5 minus 17.535. That gets us our pressure in millimeters of mercury. Okay, well, we don't want that in millimeters of mercury, so we take that answer and convert that using our pressure conversion, 760 millimeters of mercury, and that's now in atmospheres. Okay, so we put all this together in the right units, and we can take this to solve for R. So R then, we can see is equal to the pressure, so make the conversion to atmospheres, and that gets you pressure in atmospheres. And we converted our volume divided by 1,000 into liters. So now we have the right units for the numerator, atmospheres, liters, and we look and see what our moles were. That's 3.7 times 10 to the minus 3. And that's of the hydrogen moles. This is the gas. Again, because the 1-to-1 mole ratio, they're the same, but really want to emphasize all of these need to be of the gas. And then our temperature, 293.2 K. So this is the demonstration that I did last year for the class, and trying to talk while doing the experiment, do some calculations. There's bubbles that can happen, pieces of metal can break off, so lots of things that can happen, but with this came out with 0.089 for the constant. So that's pretty good. You can get pretty good results on these, and again, wanting to emphasize the correct units. That's moles K, but the main takeaway is that this constant can be experimentally determined, and that's what this experiment does. You've solved for R that you'll be using over and over in these gas law equations. So take a look at the experiment, and if you got questions, come see me during office hours.